Hey Ramblers, I'm Mr. McNulty. Welcome to Calculus. Calculus was developed over 300 years ago by Gottfried Leibniz and Isaac Newton. They worked on it independently, Leibniz in Germany and Newton, of course, in England. And since then, the 3 centuries that have passed since the discovery of the calculus, it's just proven time and time again to be an incredibly useful and an incredibly powerful tool. Whether you're studying physics or whether you're studying biology, any of the social sciences, finance, whatever field you really plan to go in from here, calculus can be a really, really useful tool for you. So I hope that you're going to enjoy this year and that you'll really get to learn the concepts behind the math, and also learn an appreciation for just the beauty of the course and the power of the material. So we're going to be doing some reading from a novel that I've come across and rather enjoyed. I think you're really going to like the course. It's really important that you don't just pay attention to how to do the problems, but really try to understand why the problems are working or what it is you don't understand about them. Calculus is full of some very, very powerful procedures, and so it's tempting to just want to learn the procedures without really understanding the greater concepts that are at work. So I really urge you in this book, or in this class this year, not to just focus on how to do this kind of problem and how to do that kind of problem. Really try to understand what's going on. One of the central themes of calculus is change, and you've been exposed to that ever since Algebra 1, primarily through the concept of slope. So we're going to look today in this first little video about some stuff you've already been over: domain, range, inputs, outputs. But we're going to be taking a look at it, recognizing that the entire year is going to build on this concept of slope. So please take good notes. I urge you to kind of rewind the video if you hit things that you don't understand. And please, you can follow along in your e-text. This covers pages 5 to 11 in the text. And the examples in this book are very good. You're going to find that they are not exactly like the problems that are assigned. So we're going to come across work in our class that the example problems are not going to mimic. That's because the book really wants you to understand the concepts involved and learn how to apply them to new situations. So without talking your ear off, good luck, and I hope this video helps. Section 1.1 in this first chapter of the Library of Functions is called Functions and Change, and I know you've been through functions probably in Algebra 1 and Algebra 2, and I'm sure again in pre-calc. And change, well, change is just another name in mathematics for slope. So this is all familiar stuff, but the whole idea of functions and change are so central to calculus that it bears mentioning again. Now please, in this course, don't focus just on how to do the problems. Really try to get that more global understanding of everything you're learning, so that you're not just knowing how to do problems, but how all the concepts fit together in the broader scheme. Let's take a look at a definition of function, something I'm sure you've been exposed to before. Here we see that a function is a rule, so it's a relationship that takes certain numbers, called inputs, and assigns them to a definite output. Now, the input numbers are called the domain of the function, and the set of resulting output numbers is called the range of the function. Now, I'm sure in your other classes we've spent a lot of time trying to make sure you weren't confused between a relation and a function. A function has one output and only one output assigned to each input. Simple enough. Okay, the input is called the independent variable, and the output is called the dependent variable. Let's move on. Here's an example of a relation. It's also a function. So the input, or the independent variable, is the date in December of 2010. You'll see that the domain here ranges from 5 through 16. The output is the snowfall in inches in Syracuse, New York. Now you'll see that the ranges from 0 all the way to a high of 14.9 over these 10 or 11 days. But for each input, there's only one output. You can see that down here on the 11th and 12th, 0 shows up twice, but that's okay. For each input, each date, there is only one value of snowfall. It just happened to show up on the same on 2 different days. That's okay. Now, this next slide shows the same data represented graphically. And that's a very important thing that this book does, and one of the reasons I like it so much. They call it the Rule of 4, where they will try to represent relationships as often as they can tabularly, or in other words, using numbers in tables. They'll try and show you a graph. They'll try to represent it with a formula. And even we try to see things in words, which can sometimes be the toughest thing to do, is to convert math into words. Here in this graph, we see that sure enough, on the 5th, the height of the graph, represented on the vertical axis, is 6.8. And if we move along the horizontal axis to the next day, we get the height represented on the vertical axis of about 12.2, I think it was. So the dates, or the independent variable, are always shown on the horizontal axis. And you'll notice that they give us the unit in parentheses. And then the dependent variable, or the range, is represented on the vertical axis. And once again, that unit is expressed in parentheses. So we would say that S is a function of the date. So snowfall in inches is a function of the date. Okay? Now, sometimes the relationship between the output and the input, or the range in the domain, is so strong that we can capture it with a formula. And that's the case here with the chirping per minute, or the chirping rate of the snow tree cricket. Interestingly enough, the number of chirps per minute can be found by multiplying the temperature in degrees Fahrenheit times 4 and subtracting 160. So let's take a look at that. That's represented on the graph because here on the horizontal axis is the temperature. That is our independent variable, and you can see that the units are in degrees Fahrenheit. The vertical axis shows us our range and is the chirps per minute, and the range seems to go from 0 to something above 400. Okay, you'll notice that scientists have found that this relationship is so strong that the rather than be a set of dots, as in the previous slide, which really don't look like they're forming any kind of a pattern, when scientists calculated the number of chirps per minute, they found that there's a very strong relationship, so much that it was linear and was very clear. Okay, all of these slides are represented in your e-text from page 2 to 6. It would be a really good idea to follow along in your e-text, or at least maybe read this afterwards. So we hit a couple of examples here about domain and range, which I urge you to read, but there's really no reason for me to take your time up and do that in the slide. So let's move on past this example of the pole vault numbers. How they show us slope. Well, maybe we'll take a minute here because it is so important. The change each year in the height of the pole vault went from 130 to 138 over 4 years. So that change in 8 inches over 4 years means that the ratio of height to year was 8 to 4, or we'd say 2 inches per year. Now you'll notice that same ratio of a change from 138 to 146, that's 8 inches over the 4 years from 1904 to 1908, shows once again the slope, or the rate of increase, was 2 inches per year. Now if you represent that graphically, you can see that it does form a line when we plot these heights versus the years, and you can see that the slope of that line is 2, because the height changed 2 inches per year. Okay, now this is really, really important, and I'm sure you've seen all this before, but you got to be really comfortable with it. In calculus, we're going to refer to the change in y as delta y, and the change in x as delta x. We want to familiarize you with that because that notation is going to change to an even smaller change in y divided by a smaller change in x. And we want you to be comfortable with this notation. So just as you've always known slope, rise over run, delta y over delta x, y2 minus y1 over x2 minus x1. Well, here in calculus, we're going to represent that y2 as f of x2 and y1 as f of x1. Okay, let's talk a little bit about another very familiar concept, this whole idea of slope-intercept form, or y equals mx plus b. So the slope is represented as m, and that is multiplying x by the slope. And then b will always be the the vertical intercept, or the y-intercept. I think the best way to think of it is the value of y when x is 0. So let's start programming our heads to think of it that way. That the y-intercept is the value of x, the value of y when x is 0. All right, let's take a quick look at these. These are a family of functions, y equals mx. Notice that all the functions that have a positive slope, like 0.5 or 1x or 2, all those functions seem to rise as we move from left to right. So as my x's are increasing, the lines are going up. Now, contrast that to all the slopes that are negative. Those lines go downward as my x's get bigger. So as x goes from negative to 0 to positive, these lines go downward. Okay, that brings us to the final slide, the difference and these two very important definitions. So please get these in your notes. A function is increasing if the values of the function increase as x increases. The function is increasing if the values of f of x increase as x increases. The function is decreasing if the values of f of x decrease as x is increasing. So you'll see, just as we saw on the previous slide, increasing functions climb as we move to left to right, and decreasing functions go downward. They fall as we move from left to right. Now, a function is called monotonic. We'll run across that in this text quite often. If over an interval or over an entire graph, it is always increasing or always decreasing. Okay, Ramblers, please go over pages 2 through 6 in your e-text. I hope this video helped you to understand the concepts that are brought up in this first section, and thanks for watching.